Optimization of multivariate functions requires the use of partial derivatives. This is particularly key in order to understand how to optimize profit and other functions given multiple outputs, which is a more realistic representation of what happens in the economy. Let's consider the bivariate function z, which is a function of x and y. In order to optimize this function, we will use a similar procedure to the steps that we use in order to optimize a univariate function. We take the first order condition, in which we calculate the first partial derivative with respect to x, and we set it equals to 0. And also, we will need to take the first partial derivative with respect to y and set it equals to 0. Because we are trying to find the optimal value x and optimal y value, we have two unknowns and at the same time two equations. Therefore, we can solve this system. The combination xy is called critical point, which will be able to optimize the function. In order to understand if the critical point that we find is a relative minimum or a relative maximum, we need to use the second order condition as we did before. However, for this case, the steps are more complex because first we need the second partial derivatives with respect to x and y, and also the cross partial derivatives. And once we have these three functions, we plug our critical points. Then we need to use the following relationships in order to classify our points. If the second partial derivatives are both greater than 0 and their multiplication is greater than the square of the cross partial, then as you can see here, this will be a convex function and therefore we will have a relative minimum. If both second partial derivatives are less than 0, but their multiplication is greater than the square of the cross partial derivative, then we will have a concave function. And therefore this will be a relative maximum. Notice that in this particular case, because we have two variables simultaneously, this is a three-dimensional graph. Finally, we add one more classification in which if the second partial of one of them is greater than 0, but the other second partial is less than 0, then our point will not be neither minimum or a maximum. Instead, this will be classified as a saddle point because, as you can see in this graph, it will be convex for one of the variables and concave for the other variable. Let's illustrate how to optimize a multivariate function by solving the following example, in which we need to find the critical points and classify them. Let's find first the critical points. In order to do that, we need to use the first order condition. So let's take the derivative of z with respect to x. Here y squared doesn't have x, so the derivative is 0. Minus, here the constant is y times the derivative of x with respect to x is 1, plus the derivative of x squared with respect to x is 2x, the derivative of 2y with respect to x is 0 because there is no x, plus 1, which is the derivative of x. And then we set this equals to 0. Now we need to take the derivative of z with respect to y. This is 2y, here x is a constant, times the derivative of y with respect to y is 1, plus the derivative of x squared is 0 with respect to y, minus the derivative of 2y with respect to y is 2, and this is equals to 0. Let's clean algebraically these operations. So this is minus y plus 2x plus 1 equals 0. And we have here 2y minus x minus 2 equals to 0. So here we can use any method because we have two equations, two unknowns. So we can solve it and find the unique solution. I think the easiest thing that we can do is we can move y to the other side. So we have 2x plus 1 equals y. And we can insert this relationship here. So this is 2 times, instead of y, we write 2x plus 1 minus x minus 2 equals 0. So this is 4x plus 2 minus x minus 2 equals 0. So this is 3x, 2 minus 2 is 0. So 3x is equals to 0. In other words, x is equals to 0. Then y star is going to be 2 times x, which is 0, plus 1. This means that y star is equals to 1. In other words, our critical point is 0,1. Now let's classify our critical point. To do that, we need to use the second order condition for multivariate functions. First, we need to find zxx. To calculate zxx, we need to remember that the second partial derivative with respect to x is simply the derivative of the first partial. Now, the first partial with respect to x, we already have it. We found it in the first order condition. So let's take now the derivative with respect to x again. So here, the derivative of y with respect to x is 0, plus derivative of 2x with respect to x is only 2, plus derivative of a constant is 0. So this is simply 2. We need now the second partial derivative with respect to y. Again, this is simply the derivative with respect to y of the partial derivative with respect to y, which we already have it too because we use it in the first order condition. So we take the derivative of y one more time. The derivative of 2y is 2. The derivative of x with respect to y is 0. Plus, and the derivative of a constant is 0. So this is equals to 2, 2. And then we need one of the cross partials because the other one would be the same. So let's use zxy. This means that we need first the partial derivative with respect to x, and that one we're going to take the derivative with respect to y. So we have already the derivative with respect to x. This is this formulation. So the derivative with respect to y of minus y is minus 1. And the derivative with respect to y of 2x is 0. And the derivative of 1 is 0. So this is minus 1. So notice that this is greater than 0 and this is greater than 0. And then we need to check if zxx times zyy is greater than zxy squared. So this is 2 times 2, and the cross partial is minus 1 squared. Now 2 times 2 is 4, and minus 1 squared is 1. And because 4 is greater than 1, the condition is satisfied. Now, let's conclude. First, we know that both second partial order derivatives are greater than 0, and the condition that the multiplication of both second partials are greater than the cross partial square. This means that this is a relative minimum point. Which it can be also interpreted as being a convex point.